Hello everyone, our group will present our findings from the characterization of perovskite films before and after passivation. Our pre includes three parts: the background and the interaction and the morphology.
Confronting the intensifying challenges of global warming and the growing imbalance between humanity's rising energy demands and the finite supply of conventional fossil resources. Transitioning the global power system from fossil fuels to renewable energy is imperative. In this transition, solar photovoltaic technology plays an indispensable role, with perovskite solar cells emerging as one of the most promising research frontiers due to their remarkable advantages such as high efficiency and potential for low cost. The working mechanism of the perovskite solar cells is in 5 steps. The first, when sunlight irradiates the perovskite material with energy greater than its band gap, the perovskite absorbs photons, generating electron-hole pairs. The electrons are extracted through the electron transport layers and are eventually collected by the metal electrode. The holes are transported through the hole transport layer and are finally collected by the transparent conductive oxide. Finally, the ITO and the metal electrode form an external circuit, generating a photocurrent microscopically. And the research motivation is showing that although the certified power conversion efficiency of single-junction perovskite solar cells has surpassed 27%, their performance remains constrained by intrinsic crystallographic defects formed during the fabrication process. These defects can be primarily categorized into two types. The first one is deep-level traps. It is included in undercoordinated halide ions, undercoordinated PB2 plus ions, late clusters, and PB2I antacid defects. And second is shallow level traps, halide vacancies, and MA plus vacancies, thus developing effective passivation strategies to precisely suppress the density of this defect status has become a critical pathway for enhancing the ultimate photovoltaic performances.
We deposit a yellow perovskite precursor solution onto an ITO substrate using the spin coating technique. This was followed by an annealing step to form the crystalline perovskite thin film. And the SEM image presented here reveals the surface morphology of our films. As you can see, the film is composed of tightly packed perovskite grains, each measure several hundred nanometers in size. The overall thickness of the film is approximately 700 nanometers, and we deposit a passivation material onto the surface of this perovskite film. And the two key observations were made from the XRD patterns. When compared to the control film, the target film shows a significantly higher relative density ratio for the 001 diffraction peak. This indicates a superior preferred orientation of the perovskite grain along the 001 direction after passivation. Furthermore, by analyzing the full width at half maximum of the 001 peak, we found that it becomes narrower in the passivated field. A narrower FWHM directly translated to better crystallinity, meaning the crystal structure within the grain has become more ordered and contains fewer defects.
The main components of perovskite films are FAI and PBI2. On the surface of the target films, FPH material passivation was performed. From the analysis of SPS data, it can be observed that for the target group, there is a characteristic peak of the C-F group at 678.8 eV, indicating that this material is indeed present on the surface of the film. By analyzing the spectra of Pb and I, it can be seen that after passivation, the peaks of Pb and I shifted, suggesting that this material interacts with PbI2. To look into this passivation material, we run II on FPH present on simple mix of FPH with PbI2. The spectra looks pretty much the same. That might be because our simple pre wasn't ideal, or maybe a straight physical mix just isn't the right way to measure it. Next, we will try another characterization method to figure out how this material actually works. That's our midterm update. Thanks, everyone.